Hi everyone. So today we're starting with this bell work problem, which is 1 over x minus 1 minus 4 over x plus 6. Now, remember back in our functions unit, we talked about adding or subtracting fractions together, especially rational expressions like this, where we've got some algebra stuff here in the denominators. And we said that, well, we would need to make a common denominator. So over here, I need to multiply by x minus 1 over x minus 1. And over here, we would need to multiply by x plus 6 over x plus 6. So we could then rewrite this with x plus 6, x minus 1 as our denominator, common denominator. We've got this minus here. We can just bring down. Over here, we've got 1 times x plus 6, which is x plus 6. But over here, we've got this 4 times x minus 1. And here's the thing. We have to take this 4 and distribute it to the x minus 1. But we also have to take this subtraction symbol. We have to take this negative 4 and distribute negative 4 to each of these. Okay, so let's do that. We've got x plus 6 minus 4x plus 4. Remember, minus and minus is plus. All over x plus 6, x minus 1. So if we tidy this up, we get negative 3x plus 10 all over x plus 6, x minus 1. Okay? That's where we've been. We've been in the place of we have two different fractions, and we want to combine them into one fraction. Well, it turns out when we're doing calculus, we get to this place where we have one fraction, and we need to go back to two separate fractions. But the thing we want to do in calculus land is impossible with one fraction, but very easy when we have two separate, or even 3 or 4 separate fractions. So then the question becomes, well, how do we do that? And the process for doing that is called partial fraction decomposition. We want to decompose this one fraction into these partial fractions. Okay, so let's take a look at this. We're starting off with negative 3x plus 10, and on the bottom, if we had FOILed this out, we would see x squared plus 5x minus 6. Okay, so partial fraction decomposition takes place in 4 cases. And this one is case 1. Case 1 is non-repeated linear factors. Okay? And by factors, we're talking about factors of the denominator. So, the first thing we always want to do here is factor the denominator. Sometimes we'll be given the denominator in factored form, other times we will not. So the first thing we want to do is factor the denominator. All right, well, I know how this denominator factors, but even if I wasn't comfortable with it, I would apply my factoring skills, x plus 6, x minus 1. Now, step 2. Put a letter A, B, C, etc., over each denominator. So, over each factor, there we go, factor in the denominator. So I've got these two factors, and so I'm going to say, well, this is a over x plus 6 plus b over x minus 1. Now, you could also write b over x plus 6 and a over x minus 1. It really doesn't matter. It's completely arbitrary. The student who does this versus the student who does this student's a will be this student's b. The end result will be the same regardless of which way we start the problem, okay? So that's step 2. Put each of these over. Now, so the problem looks like this at this point. Negative 3x plus 10 over x plus 6, x minus 1 equals a over x plus 6 plus b over x minus 1. And now this looks like one of those rational equations that we were solving back in the Algebra Basics unit. And so now we want to do step 3, multiply every, not some, every term by the least common denominator. The least common denominator is not all this times this times this. The least common denominator is this. Our least common denominator is always going to be our original denominator. Okay? Always use that original denominator. It is the least common denominator. So I'm talking about multiplying everywhere by x plus 6, x minus 1. X plus 6, x minus 1. X plus 6, x minus 1. Because when I do this, these cancel, this cancels that, and this cancels that. And so now, just like when we were in Algebra Basics, I'm left with an equation that has no fractions. A x minus 1 plus b x plus 6. Okay? Now, from here, there are two paths we can take for step 4. Step 4 is going to be find A, B, C, etc. Find our constants. And we've got two ways to do that. We can either use what I call magic numbers, because they make things disappear, or we can use something I call systems. Okay? Let's take a look at using magic numbers and systems to solve this set of coefficients a, b in our problem. But sometimes we have a, b, c, d, e, f. Okay, so right now we're looking at minus 3x plus 10 equals a x minus 1 plus b x plus 6. Let's take a look at systems first, because systems is very useful. I wouldn't do case 4 without systems, but in case 1, like this problem, systems are less helpful. They're not hard, just a little less helpful. The all magic numbers approach is a little easier in case 1. So we'll look at both, but we'll start with the harder one, or the, yes, I think it's not harder, but longer taking one. All right, so with systems, we want to distribute. So I'm going to multiply through, And now my equation will look like negative 3x plus 10 equals ax minus a plus bx plus 6b. All right? Now, what do? Well, this is called systems because we want to make a system of equations. I'm going to gather together all the stuff on both sides of the equation, but I'm going to keep the equation, all the stuff that has an x. And I'm going to make an equation out of it. Negative 3x equals ax plus bx. And then I'm going to take all the stuff that doesn't have an x and gather it together in one equation. And so I'm going to have 10 equals negative a plus 6b. And we haven't gone to solving systems yet, but you did do systems last year. So what do we remember about solving systems? Well, we could use elimination or substitution. I don't recommend using graphing. Ooh, there's one other thing I want to do. See how all of these terms have an x? Well, I want to divide everywhere by x. And so now I'm going to end up with negative 3 equals a plus b. And here I have 10 equals negative a plus 6b. And I'm going to add these two equations together. Okay, so negative 3 plus 10 is 7. A plus negative a, they cancel. And b plus 6b is 7b. I know to add the equations together when the signs on the letters are opposite. If one is plus and one is minus, I'm going to add. If they're both the same symbol, I'm going to subtract. So I divide by 7, and I find that b equals 1. If I take b equals 1 and plug that into either of these equations, I'm going to get a value for a. So we know here that negative 3 equals a plus b, and I'm going to replace b with 1. Negative 3 equals a plus 1. I'll subtract 1 from both sides and get negative 4 equals a. Now, we're almost done. That was step 4, finding a, b, c, etc. And step 5 is write a, b, c, etc. over the original denominators. So remember these, how we started with a over x plus 6 and b over x minus 1? Well, we've now found our b and our a, and we're not done until we write negative 4 over x plus 6 plus 1 over x minus 1. And look, we got back to where we started our original problem. This was the problem that we had started as our bell work, when we wanted to take these two fractions and combine them. So this was doing the solving part for a, b, and c using systems, right? We distributed, then we gathered all the x stuff into one equation. I should say the x to the first stuff. And we gathered all the stuff that didn't have an x into another equation. We divided over here to get rid of the x's, and then we took those two equations together. We eliminated a variable, and we plugged that value back into either equation to solve for our other variable. That's systems. Works fine. Don't forget at the end, you're not done when you found a and b. You actually have to plug the a and b back into your original. Here, where you factored, where you put a letter over each of those factors in the denominator. But now let's take a look at magic numbers. Magic numbers is starts at this same place. When we get to this moment, we can use magic numbers or systems. We're still going to have to write two fractions. We're still going to multiply every term by the least common denominator, and that will always bring us to this place. Okay, so let's see what happens when we use magic numbers instead. And remember, I said that they were magic numbers because they make things disappear. So we've got negative 3x plus 10 equals a x minus 1 plus b x plus 6. Okay, and I said I really like magic numbers for case 1 because things go pretty fast. So this is magic numbers. Okay, so a magic number is a number that makes things disappear, and in this problem I claim x equals 1 as a magic number. How come? Because 1 minus 1 is 0, and 0 times a is 0. Poof, we made a disappear. So when I plug in a 1, 1 minus 1 is 0, 0 times a is 0, all of this is gone. I still need to plug in my 1 for these x's, so over here I have negative 3 times 1, which is negative 3, plus 10 is 7. Here I have 0, plus b times 1 plus 6. Oh look, 7b equals 7. And I get b equals 1. What's another magic number? Well, what would turn this into 0? If I used x equals negative 6, that's a number that would turn this into 0, and therefore 0 times b, poof, b disappears. So this is my second magic number, and I'm going to plug a negative 6 in for all x's. If I plug a negative 6 in here, I have negative 6 times negative 3, which is positive 18, plus 10 is positive 28. If I plug a negative 6 in here, I have negative 6 minus 1 is negative 7a. And if I plug a negative 6 in here, I get 0 times b, so the b's go away. I divide by negative 7, a equals negative 4. Well, look, those are the same values, and it was a little less work than using systems. Sometimes it's a lot less work than using systems, and so I encourage us to use magic numbers, okay? So what do we got here? We've got then negative 4 over x plus 6, because remember, we always have to write that last step, 1 over x minus 1. Of course, this would be the same as 1 over x minus 1 minus 4 over x plus 6. And that's really where we started with our bellwork problem today. All right, let's take a look at another type, case 1 problem. I recommend you practice this one and see how far you can get with it. So let's say x over x squared minus 5x plus 6. Well, the first thing we said we needed to do was always to factor the denominator. Good thing we practiced our factoring. X minus 2, x minus 3, with an x on top. The second thing we said we needed to do was put a letter over each of these factors. So now I'm looking at x over x minus 2, x minus 3 will be a over x minus 2 plus b over x minus 3. Okay, then we said we would multiply every term by the least common denominator, and I said that this would always be our least common denominator, and you should use that. Students who ignore this step and actually use this, yet they find they can't actually solve for the constants a and b, and they get stuck and upset and sad. So please make sure you multiply everything by the least common denominator, which is right here. So I'm going to multiply everything by x minus 2, x minus 3. Everywhere. And yes, I'm going to write it out because I don't want to miss anything. This helps cut down on my mistakes, which is why I do it. Okay? I notice that these cancel these. I notice that this cancels this, and this cancels that. So now I've got x equals a x minus 3 plus b x minus 2. I'm not going to use systems in this one. We're going to get plenty of systems practice later with cases 3 and 4, where I don't really use magic numbers and I do use systems. Okay, so let's say, what are magic numbers here? Well, what's something that would make this turn into 0? Well, if x were equal to 3, And when I choose x equals 3, because poof, this will turn into 0 and 0 times a will make a disappear, I have to plug that x in for all the x's, here and here and here. So 3 equals 3 minus 3 is 0, 0 times a, poof, that's gone. We've got our b, and now we have 3 minus 2. Well, 3 minus 2 is 1, so 1b is 3. Now, what's another magic number? Well, we used x equals 3 to make this disappear. What could we use to make this disappear? How about x equals 2? Again, I have to plug this 2 into all the x's of this statement. So 2 equals 2 minus 3 is negative 1 times a. And then 2 minus 2 is 0, and 0 times b, poof, b disappears. So negative a is 2, which means positive a is negative 2. So my partial fraction decomposition is going to be negative 2 over x minus 2 plus 3 over x minus 3. There's my partial fraction decomposition for this fraction. Okay? That's the kind of thing you need to be able to do on our next quiz very comfortably. We'll have a couple of days practicing this and reviewing our rational function graphs before we get to our next quiz, which is just on those two topics. Now, I mentioned that there were 4 cases, and case 1 was non-repeated linear factors. Well, case 2 is repeated linear factors. Case 2. Repeated linear factors. And what do I mean by that? I mean the factor has a multiplicity greater than 1. So, for example, if I see 5x plus 3 over x minus 1 squared. See the squared? So this is a repeated linear factor because I've got a 2 there. So how would I do this? Well, I would do 1 over x minus 1, and I would do b over x minus 1 squared. Whatever power this is, I have to have all the powers leading up to that power as well as that power represented as fractions. So if this were a 3, I would need a c over an x plus 1 to the third. Sorry, an x minus 1 to the third. And if this was a 4, then I would need a d over x minus 1 to the fourth. Please note, I have to have all the power possibilities. I don't know. It may turn out that some of these letters are zeros, and those terms go away. Maybe it's only these 2 terms, maybe it's these terms, maybe it's these 3 terms. I'm not going to know how this decomposes unless I cast the broadest possible net to start with. So whatever this power is, that's how many fractions I should expect with that factor underneath to various powers, right? I have to represent all the powers too. First power, second power, third power, fourth power. Okay, so how would I set up this one where I had negative x plus 1 over x plus 2 squared? Well, this is only a 2, so I'm going to have an a over an x plus 2 to the first, and a b for x plus 2 to the second. All right? Now, I still have to solve for these letters. Don't get me wrong. We still have to go through the process of partial fraction decomposition. So let's take a look at that. We've got 5x plus 3 over x minus 1 squared. And I said the setup would be a over x minus 1 plus b over x minus 1 squared. Again, this is my least common denominator. Not this times this times this. Don't do that. Stop it. Watch the actual video. Hear me nagging you. Write it down in your notes. Don't do that. Instead, this is my least common denominator. So I'm going to multiply everything by x minus 1 times x minus 1. X minus 1 times x minus 1. Okay, and so now, what canceling do I have? Well, this cancels that, and this cancels that, and this cancels that. And so what am I left with? Well, there's not a lot left. There's 5x plus 3 equals a x minus 1 plus b. Now, this is where magic numbers starts to be problematic, because I only have one magic number. Okay, so my magic number would be x equals 1. I put in a 1 here. I get 5 plus 3 is 8. I put in a 1 here. 1 minus 1 is 0. 0 times a, poof, a disappears. And now I've got just a b. Great, I know what b is equal to, but I don't know what a is equal to, and I don't have any more magic numbers. So when that happens, I have to use a not-so-magic number, which is pick any number you want. I'm going to use x equals 2 and not x equals 0, and I like x equals 2 because 2 minus 1 is 1. And I'd rather have 1a than negative 1a. If I used x equals 0, I'd have 0 minus 1 or negative 1a. Yes, you can use any number you want that's not the number you've already used. So 0 would be fine, 2 is fine, 77 would be fine, but I'm not making 77 times 5 over here. But I will plug in a 2 over here. So 2 times 5 is 10, plus 3 is 13. And then over here we have 2 minus 1 is 1a, and we still have our plus b. Well, we know b is equal to 8, and so we get 13 equals a plus 8. And we'll subtract 8 from both sides, and we'll get that a equals 5. So how does this decompose? Well, we've got 5 over x minus 1 plus 8 over x minus 1 squared. So that's using a magic number and a not-so-magic number. It was not-so-magic number because nothing disappeared. It was a magic number because when we plugged 1 in, a disappeared. Okay? Let's take a look at the same problem from this step using systems. I promise systems is going to have value. So we remember with systems we distribute. 5x plus 3 equals ax minus a plus b. And then we want to group the same stuff together. So we'll take all the stuff with x. We could even divide both sides by x, and that gives us a equals 5. And we'll take all the stuff that doesn't have an x and put it together. 3 equals negative a plus b. We know a is 5, so negative 5 plus b equals 3. And we'll add 5 to both sides. Hey, look, we got those same values. We've got now 5 over x minus 1 plus 8 over x minus 1 squared. Remember, we have to take our a and b values and plug them back in up here. So that was using systems, and systems didn't seem so bad this time. It seemed a little easier than when we did it in case 1. And systems was actually kind of easy, maybe easier or as easy as magic numbers, I find in case 2. Let's take a look at doing just a second practice case 2 problem. And then I want a transitional problem. Okay? So our second case 2 problem, negative x plus 1 over x plus 2 squared. Well, I'm going to have a over x plus 2 and b over x plus 2 squared. So, where do we go from here? We multiply everything by the least common denominator. X plus 2, 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 x plus 2. Now, I agree, this takes a long time to write out, and I know that many of you are not going to do it. But if you're prone to making little mistakes, I would do this step. I would write this out, because really a lot of mistakes happen here when people build the wrong equation without fractions to solve. So we've got an negative x plus 1, an equals a x plus 2 plus b, because both of these cancel with both of those. I'm going to use systems here, and remember with systems we distribute. So we have negative x plus 1 equals ax plus 2a plus b. And then I'm going to group the same things together. So I get negative x equals ax. If I divide both sides by x, I get a equals negative 1. And now I'm going to take the things that don't have an x and group them together. And so I'm going to have 1 equals 2a plus b. But we know that a is equal to negative 1, so let's plug that in as well. 2 times negative 1 plus b. And I get 1 equals negative 2 plus b, or b equals 3. Remember, when you found these coefficients, you're not done yet. You still need to write them over the original fractions. So we're going to have negative 1 over x plus 2, and we're going to have a 3 over an x plus 2 squared. Okay, so there's case 2, repeated linear factors. Well, we could also run into a combination of cases. So, for example, if we look at x plus 2 over x to the third minus 2x squared plus x. Okay, so the first thing we need to do is factor, right? We factor that denominator. I know there's a GCF I can pull out from each of those terms. And so I'm going to have x plus 2 over x squared minus 2x plus 1. But wait, I'm not done factoring. Remember, we have to factor completely. We want some linear terms down here. So when I factor this trinomial, I'm going to have x minus 1, x minus 1, with that original x plus 2 on top. This can be combined to be x minus 1 squared. And so look, here's our case 2, our repeated linear factor, but we've only got one of these. This is case 1. So I've got an a over an x. That takes care of this one. But now I have to take care of this. I need b over x minus 1, and I need c over x minus 1 squared. Okay? So then the process is the same. We multiply everything by the least common denominator. Here it would be x minus 1, 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 and x minus 1, x minus 1. So this cancels all of that, leaving me just x plus 2. Over here, this cancels that, leaving me a x minus 1 times x minus 1. This cancels one of those, leaving me b x minus 1. And here these cancel all of these, leaving me c times x. All right, well, I see two magic numbers. I see x equals 1 is a magic number, but x equals 0, 0 times all this stuff is 0. Poof, b disappears. 0, c disappears. So I've got two magic numbers, but I've got 3 letters to find. So either I'm going to use systems here, which is going to take some time because I'm going to have to FOIL and distribute and group things. And so I really still prefer with this type of case 2 problem to use magic and not so magic numbers. So that's what I'm going to do here. I'm going to say, let's make x equal to 1, because when I plug in a 1, these will turn into zeros, this will turn into zeros, and all this will disappear, leaving me with just 1 times c over here, and 1 plus 2 is 3. So that was a really great magic number because so much disappeared, and we just had to plug the 1s in at the ends. And what about our other magic number, x equals 0? Because that will make this disappear and all this disappear. If I plug in zeros here, I'm going to have 0 minus 1, 0 minus 1. Negative 1 times negative 1 is positive 1a. And over here, 0 plus 2 is 2. So I've already got 2 of my 3 coefficients. I've got a, I've got c, but I've run out of magic numbers, so I'm going to have to use a not-so-magic number. I'm going to use x equals 2. So 2 plus 2 is 4, plus a. 2 minus 1 is 1. 2 minus 1 is 1. 1 times 1 is 1. Oops, that's an equal sign. So really I'm just multiplying that by 1. 2 times 2 minus 1. 2 minus 1 is 1, so 1 times 2 is 2b. And then we're plugging in a 2 for x, and we get 2c. So let's plug in what we know. We know a equals 2. We know c equals 3. 4 equals 2 plus 2b plus 2 times 3 is 6. I get 4 equals 8 plus 2b. I subtract 4 from both sides. Subtract 8 from both sides and get negative 4 equals 2b. So we know that when we divide both sides by 2, we get b equals negative 2. So our final answer, our partial fraction decomposition, we take these 3 coefficients and we plug them back into our original setup. 2 over x plus negative 2 over x minus 1 plus 3 over x minus 1 squared. Now, right here, you might see this written that way, and that's fine too. I usually write it this way because students say, but that b value was negative 2, and they really want to see the negative 2 there. Okay? So that's case 2. Now, there are cases 3 and 4. Let's take a look at those briefly. Case 3. Case 3 is non-repeated, irreducible quadratics. So instead of linear factors like we've been dealing with, we're going to have things that don't factor but are quadratics. Okay, or they factor but only with imaginary numbers. For example, 3x minus 5 over x to the third minus 1. Well, remember we're supposed to factor first. So we get 3x minus 5 over x minus 1, x squared plus x plus 1. Mr. Kukla, how did you factor that? This is a difference of cubes. I had to remember the difference of cubes factoring from our Algebra Basics unit. Yes, I did. Yes, I do need that now. Yes, you did need to memorize it back then. You still need it right now. Now, I also said when we were talking about a difference of cubes that this part here wouldn't factor with real numbers. This is our irreducible quadratic. This is just a plain old linear factor. This is not repeated, so this is case 1 over here, and I can just write a over x minus 1. But this is my irreducible quadratic. This is what makes this problem a case 3 problem. I've got this irreducible quadratic. I can't factor this to linear factors. So I'm going to do x squared plus x plus 1. Well, what goes on top? Well, what goes on top is 1 degree less than this. This is second degree, so I need a first degree thing on top. So I'm going to have bx. And then what I'm making here is a first degree thing, a linear thing. But not all linear equations pass through the origin. There might be some shift up or down. So I need a bx plus c. Oh, you're not going to like that, are you? Look, what if we had this? What if we had x squared plus 1 times x squared plus 4. Okay, these are two irreducible quadratics. If we had minuses, they'd be difference of squares, and I could take them further, but they're pluses, and they would only factor with imaginaries. So we're going to say these are irreducible quadratics. And I'm going to write ax plus b over x squared plus 1. And I'm going to write over this one, x squared plus 4, cx plus d. Okay, this is case 3. Non-repeated, irreducible quadratics. Okay, I can't factor these quadratics with reals. And notice how this is second degree, and this has to be first degree on top. But not all first degree equations pass through the origin, so we need to take into consideration that maybe there was a shift up or a shift down. It may turn out when we're solving for one of these that we end up with this going away or this going away. So don't be surprised if one of these letters turns out to be 0. That's okay. We don't know what the answer is going to be, so again, we have to cast the broadest possible net just in case. All right, so let's solve this first one. Okay, we're going to multiply everything by the least common denominator, which is again this. This is my least common denominator. So x minus 1, x squared plus x plus 1, and then here x minus 1 times x squared plus x plus 1. Okay, so what canceling is there? Oh, I didn't multiply this one. X minus 1, x squared plus x plus 1. Well, I can see that these will cancel these, and this will cancel that, and this will cancel that. So what does that leave me with? Well, on the left-hand side, I've got 3x minus 5. On the right-hand side, I've got my a times this stuff. X squared plus x plus 1. Now we've got a plus, and we've got this bx plus c. And I'm going to tell you, you should really put that in parentheses, because now I have to multiply by x minus 1 that was left over. Many students do this, and they get in trouble because they only distribute the c to these things, but really this is a foiling problem. Okay? So I've got two methods of doing this problem from here. I can use magic numbers or I can use systems. Now when I look at this case, I see, well, one magic number would be 1 and another magic number would be 0. So I could use two magic numbers, and because I have 3 letters, a not so magic number, or I could use systems. And I think maybe I should take a look at both just to see which might be easier in this case. Okay, so let's take a look with magic numbers. Let's x equal to 1. So 3 minus 5 is negative 2. 1 plus 1 plus 1 is 3a. 1 times b is b plus c. But wait a second, if I plug the 1 in here, 1 minus 1 is 0. And that makes all of this go away. And so I know that a is negative 2/3. All right, what about x equals 0 as a magic number? Because then b will disappear. So that goes away. This goes away. I have negative 1 times c, which is negative c. I put in 0 for these x's, and I end up with 1a. And I put in 0 for this x, and I get negative 5. Now we know that a is negative 2/3. So let's add 2/3 to both sides. This is negative 15/3 plus 2/3 is negative 13/3 from minus c. So plus c would be positive 13/3. Isn't it interesting how this thing that you learned how to do in middle school, this adding and subtracting of fractions, is terribly, terribly important here? And the reason you did so much of it in middle school is so that you could actually not get bored, but get really comfortable with it. It should not be difficult for you to say that this is the same as minus 15/3 plus 2/3 for negative 13/3. But if it is, take the time to make that common denominator so that you can, in fact, add 2/3. Okay? So we've got our a value. we've got our C value. We still need to find a B value with some kind of not-so-magic number. And again, because I have an x minus 1, I like using 2 because 2 minus 1 is 1. So I'm going to say x equals to 2. Okay, so 2 times 3 is 6, minus 5 is 1. And 2 squared is 4, plus 2 is 6, plus 1 is 7. And then here, 2 minus 1 is 1. And then we've got 2b plus c times that 1. Well, 1 times this stuff is really just that stuff. So all I need to concern myself with is that. All right, let's plug in the a and the c that we know. 1 equals 7 times negative 2/3 plus 2b plus 13/3. Okay, so we've got 1 equals negative 14/3, right? Because 7 times negative 2 plus 2b equals 13 plus 13/3. Minus 14/3 plus 13/3 is negative 1/3 plus 2b. And so we'll add 1/3 to both sides and we'll get 4/3 equals 2b. But we want to divide both sides by 2. And we can cancel a 2 here. And so we know that b equals 2/3. So b is 2/3, a is negative 2/3, and c is 13/3. And so we have to go back up to this step. Wish I hadn't noticed that. We have to go back up to this step and write our answer. In fact, I'm going to switch boards right now because there's too much information on that board that I still want. Okay, so we've got a over x minus 1 plus bx plus c over x squared plus x plus 1. And we're plugging in our negative 2/3 for a. And what do we have for b? We've got 2/3 for b. And what do we have for c? C was 13/3. Now, this is a fine answer, but this is not the answer you're going to see in the back of the book. See this denominator? Yeah, the back of the book says you should write this like that. And see how these both have that common denominator? So the back of the books is going to show you this. I will either accept this one or the back of the book one. They're both fine by me. Okay. All right. So there's our answer. And I'd like to get to that same place by using systems. Okay. We did magic numbers and not so magic numbers here. And remember we had bx plus c times x minus 1 here. Well, with systems from this point, remember we need to do some multiplication. All right, I need to FOIL here and distribute here. So I'm going to have 3x minus 5 equals ax squared plus ax plus a. And here I have to FOIL. I'm going to have bx squared plus cx. Negative 1 times bx is minus bx. Negative 1 times c is minus c. Wow, look at all that stuff. Okay, so, you know, we've got this, and we're supposed to group things. So I'm going to take all the x to the first stuff and group the x to the first stuff into an equation. And so I'll have 3x equals ax plus cx minus bx. And then if I divide everywhere by x, I get 3 equals a plus c minus b. So there's one equation. Now, what about another equation? Well, let's take all the stuff that doesn't have any x's and put it together in an equation. Negative 5 equals a minus c. Okay? So there's our second equation. Now, I think we should make a third equation because, look, we've got all this x squared stuff. But Mr. Kukla, there's no x squared stuff over here. I know. So that's why I'm going to use a 0 over there. There is none. And 0 equals ax squared plus bx squared. And if I divide everywhere by x squared, I get 0 equals a plus b. So your book really likes the systems approach, and they would encourage you to use systems here. So here's what I'm going to do. I'm going to take these and use these as helping equations. I'm going to solve this for C. I'm going to solve this for B. And then I'm going to plug those into this equation. All right, so this is what's going to happen. I'm going to say that C equals a plus 5. And over here, I'm going to subtract a from both sides and say that b equals negative a. And now over here, I'm going to plug in my c and my b. So what's this going to look like when I do that? I'm going to have 3 equals a plus our c, which is a plus 5, minus our b, which is negative a. So this is going to be 3 equals a plus 5 plus a, or 3 equals 3a plus 5. If I subtract 5, I get negative 2 equals 3a. I divide by 3, I get a equals negative 2/3. I plug this a back into each of these equations to find out that c would be negative 2/3 plus 5, which means negative 2/3 plus 15/3, or c is 13/3. And then finally over here, we know that a is negative 2/3, but b is negative a, so we know that b is positive 2/3. So we can get the same coefficients by using systems, right? Or by using magic and not so magic numbers. I'm never going to specify a method. You use whichever one you prefer. Okay? So let's do 2 more problems, and then we'll call it a day. The first problem is this one. 3x squared plus 4x plus 10 over x squared plus 2, x squared plus 1. Okay? So again, I have to start off with this. This is one of my denominators. Here's my other denominator. Because these are irreducible quadratics, I can't factor them further to linear factors without using magic numbers. I need something that's 1 degree less up top. So ax plus b, and I've already used those letters, so over here I have to have cx plus d. We multiply everywhere by the least common denominator, and again, the least common denominator is not this times this times this times this. This is the least common denominator. X squared plus 2 times x squared plus 1. I'm going to multiply everywhere by x squared plus 2, x squared plus 1. X squared plus 2, x squared plus 1. So this cancels all of that. I'm left with 3x squared plus 4x plus 10. Over here, the x squared plus 2's cancel, leaving me with ax plus b. Notice I'm putting it in parentheses because I have to multiply it with x squared plus 1. And then over here, we see that the x squared plus 1's cancel, leaving us with cx plus d over times x squared plus 2. Okay? So, now what? Well, let's think about magic numbers. What magic numbers do you have? And right now, there's nothing that's going to make that disappear, and there's nothing that's going to make that disappear, because these parabolas are never equal to 0. They've been shifted up. The only magic number I have is 0, and that's a problem, because I've got one magic number, but 4 letters to find. So even if I start with magic numbers, I'm going to end up having to do systems anyway. So I might as well just bite the bullet and start with systems. Ooh, I wish I hadn't done this. Alright, so that means foiling over here. What do we get when we FOIL? We get 3x squared plus 4x plus 10 equals ax to the third plus bx squared plus ax plus b plus cx to the third plus dx squared plus 2cx plus 2d. All right, and now we want to do our grouping thing. Okay, so I'm going to take these x to the thirds. There's no x to the thirds over here, so I get 0 equals ax to the third plus cx to the third. And if I divide everywhere by x to the third, I get 0 equals a plus c. There's one equation. Now, a second equation. How about the x to the second stuff? Okay, so I've got x to the second, I've got x to the second, I've got x to the second. So I know that 3x squared equals bx squared plus dx squared. And that's going to then be, when I divide everywhere by x squared, that's going to be 3 equals b plus d. Second equation. That's a b. Let's take the x to the first stuff. Okay, x to the first. We've got 4x, ax, 2cx. So we've got 4x equals ax plus 2cx. And if we divide everywhere by x, we get 4 equals a plus 2c. Okay. And finally, this stuff that doesn't have any x's at all. That, and that, and that. And we could say that 10 equals b plus 2d. All right, well, this isn't as bad as I feared, because look, we've got two equations that just have a and c, and two equations that just have b and d. So we can solve these with elimination. Okay, we're going to have 4 equals a plus 2c, and 0 equals a plus c. Remember, I said when these coefficients have the same sign, they're both positive a, we subtract. So 4 minus 0 is 4, a minus a cancels, 2c minus 1c is c. Now I know what c is, and I can plug that c into either of these equations to find out that a is negative 4. Okay? Now let's take a look at the second set of equations. Okay, we've got 3 equals b plus d, and we've got 10 equals b plus 2d. Here they're the same, so I'm going to subtract. 3 minus 10 is negative 7. b minus b, they cancel. d minus 2d is negative d. So I know that positive d would be positive 7. I'm going to plug this back into either of these equations. 3 equals b plus 7. I'm going to subtract 7 and get b equals negative 4. So my final answer then, right, because I've got to write this back on top of these originals. Let's take a look at these originals again. We had originally ax plus b over x squared plus 2 plus cx plus d over x squared plus 1. We found out that a was equal to negative 4, b was equal to negative 4, excuse me, over x squared plus 2, plus c was equal to positive 4, and d was equal to 7 over x squared plus 1. So there's my answer. Okay, so that's case 3, irreducible quadratics. Remember, we could see case 3 combined with other cases, like we could see a setup like this. What if we had 3x minus 5, but this time we had x minus 1, x squared plus 1. Okay, so these are case 1. We got a over x plus b over x minus 1. But this is the irreducible quadratic, so we would need a cx plus d over x squared plus 1. And if I had this problem, 3x minus 5 over x minus 1, x plus 1 squared. Well, now this is case 1 over here and case 2 over here with the repeated linear factor. And I would have a over x, b over x minus 1, c over x plus 1, and d over x plus 1 squared, right? Because I have to represent all the possible powers of this one. This would suck. Well, 1, 2, 3 magic numbers. I would only need one not so magic number. It would really suck to do that with systems. Ooh, don't do that with systems. And then what if we had this one? X minus 1 squared, x squared plus 1. Okay, so I have case 1, I have case 2, I have case 3. I've got a over x plus b over x minus 1, c over x minus 1 squared, and here's my irreducible quadratic, plus dx plus e over x squared plus 1. Ew, Mr. Kukla. All right, now seems like a great time to talk about case 4. Really, I would write these down because students get mixed up on these setups all the time. They're comfortable solving, but the setting up seems to be a challenge. So pay attention to, that's an irreducible quadratic, that's a repeated linear factor, that's case 2, and here we have a case 3, a case 2, and a case 1. All right, let's go now to case 4. I don't think we see any case 4s. I just want to introduce it to you. Case 4 is repeated irreducible quadratics. And so this is going to be the situation like 3x minus 5 over x squared plus 1 squared. So just like in case 2 where I had to represent all the power possibilities, I have to have this one to the first and also this one to the second. And remember, what goes on top is 1 degree less than this factor. So we need ax plus b. And here, I know you're thinking that's a 2. Shouldn't that be x to the third up there? No, it's 1 degree less than this thing. This is that factor that's being squared. So we're going to have plus cx plus d. Okay, that's case 4. And if we had a 3 here instead, well, we would just say we're going to have an x squared plus 1 to the third with an ex plus f on top. All right, 4 cases. Guess what we're doing next? We're going to be practicing the heck out of all this stuff. All right, you might want to take some notes on this video. We definitely need all this stuff tomorrow. Take care.